The title of the conference is First Passage Percolation and Related Models. So this is a related model talk. This is a joint work with my our former students, Hongbin Chen and Ling Li. So this is not really about first passage percolation or last passage percolation, but first I'm going to explain a little the connection. I figured out that not many people have talked about polymers at this conference, so I will have to say a couple of words. So that's about one slide. But the main material here is about directed polymers, and this is a list of keywords that I will be mentioning throughout. And directed polymers are given by Gibbs, by certain Gibbs distribution. So this is a random environment problem. So polymers are random chains of monomers interacting with the media, with the random media. And my goal is to understand their behavior in like infinite length or infinite volume polymers. That's the goal. And the new thing in this talk compared to my previous work is the dynamical viewpoint. And I will talk about stochastic gradient flows in infinite dimensions and invariant measures for these flows. And I will talk about monotonicity and one-force, one-solution principle. So this work began, the initial motivation was stochastic PDEs of Hamilton and Jacobi type. And so it's related to stochastic Burgers, KPZ, and heat equations. But I will not talk about stochastic PDEs at all in this talk. So first, so this is I think my only last passage percolation type slide. And so this is what I'm going to consider. The setting is sort of similar to last passage percolation, except this is a model with discrete and continuous component. And so the time is discrete here, and the space is continuous. And I'm interested in these chains that I will call eventually, I will call them polymers. But the main ingredient here is this energy function. So to each path, you associate an energy, and the energy is composed of two contributions. So this is the term, the energy term of interaction of the polymer with itself. So it interacts with itself only through the nearest neighbor interaction. And also the polymer interacts with the environment. So there is this external potential on each of these for each time. So this is time 0, 1, 2, and so on. This is space. So at each time k, I have a realization of a potential Fk. So now it depends on the spatial component. And I will assume that these potentials are IID in k, and they will be mixing in x. And so the first question you could ask is how do minimizers of such an energy behave? So this is the last passage type percolation question. You can fix 2 points, x0, xn, and just find the path, typically is just one, that minimizes this action or energy. And of course, you're interested in the behavior of these paths when time n goes to infinity. So you can view this as time, or you can use this just as an extra spatial coordinate. So we studied a model like this, first with Erika Toren-Kostya-Hanin, and then that was a model that was not quite this. And then I wrote a paper about concretely this model in 2016. And so the questions that we are asking is, that we were asking in these papers, as n goes to infinity, you can take this point xn to infinity along a direction, and what is the result of this limiting procedure? And so we constructed semi-infinite one-sided geodesics, and we understood certain things about their mutual behavior, and then we were able to apply this to the ergodic theory of the Burgers equation. Now, the last passage percolation type model can be viewed as a zero temperature version of a polymer model. And so in most of this talk, throughout the rest of the talk, I will be talking about the positive temperature case. But this is the zero temperature introduction, and this is the connection to the main topic of this conference. So polymers. So this energy that I introduced, it is still the main player here, but now instead of considering the minimal path that connects these 2 points, we're now considering the Gibbs distribution with positive temperature associated to this energy. And so it means that I'm interested in the behavior of this measure, whose density with respect to the Lebesgue measure is given by this standard formula from statistical mechanics, where the density of each path is proportional to minus beta times the energy of this path. So energy is just the same. Beta is anything positive. Beta is actually the inverse temperature. T that will occur in this talk, it is the temperature itself. So they are reciprocals of each other. And the connection with the zero temperature model is that as the temperature goes to zero or inverse temperature goes to infinity, so this cooling happens, and the entire Gibbs measure concentrates on the minimizer. There's just one minimizer. Typically, there's one. So these measures, these are very general words. So they penalize the configurations with high energy. So it means that most of the mass that this energy assigns, it is concentrated, located at low levels of this energy, right? So if this E is small, then this is a relatively large number. And if this E is large, then it's then this exponential of this negative number is very small, and so the paths will not go there. Okay, so these are these general words, and that's the finite length or finite volume picture. In that picture, well, it's the same picture, but in this picture, I fixed the point x0 and I fixed point xn, and I consider this measure that depends on the realization of the potential. So this is going to be random, and once you fix the realization of the external potential, then you also have a distribution on this path now. So this is two layers of randomness. And so all these paths, they connect these 2 points. And so that's a point-to-point polymer measure. We're interested in studying the infinite length version of that. And in infinite volume, it gets trickier, as always with the Gibbs distribution. So you cannot just say, let's consider this energy and take just let n be infinite and just compute the sum of all these terms, because you will get just infinite numbers, and that doesn't make sense. Doesn't let you to define any meaningful distribution on infinite paths. So instead, what the standard viewpoint is that one should look at this Dobrushin-Lanford real condition, and it says that we should view the point-to-point polymer measures as conditional distributions given the path outside of the interval of finite length. So what this says is the following: I will call a measure on paths indexed by all natural numbers. Well, there's also a zero, but zero is going to be fixed. So you have a measure on all the on infinite paths. I will call that an infinite volume polymer measure if for each positive n, for each natural n, the distribution on these paths conditioned on the path outside, on the tail of the path, if that conditional distribution coincides with the point-to-point Gibbs measure that I described in the previous slide. And this is only a restating the DLR condition for this concrete model. And so, so the general words that one should say is that we all know the Kolmogorov consistency theorem, where the existence and uniqueness of the process with infinitely many components is derived from consistency of finite dimensional distributions But here it's a different way of, a different attempt of prescribing the infinite dimensional distribution. So there is, in principle, we don't know if there is a unique measure that satisfies this DLR condition. Maybe there is none. Maybe there are infinitely many of them. So this definition itself doesn't answer these questions. So before I start stating results, let me just devote this page to these conditions on the random environment. So the random environment is given by this random potential. What I'm assuming is that it's stationary, both in space and time. Moreover, in time, I assume that you have IID copies of the same process. In X, there is some form of mixing that we need to assume. Finite dependence range is just fine. We need to impose some exponential moments. We need to impose some smoothness in X. And there is an extra condition that I'm going to discuss later. But if you need an example, for example, you can take a smooth Gaussian process with finite dependence range, or you can take Poissonian points and convolve them with the kernel in the X coordinates. So you will have a nice process that the stuff that I'm going to talk about works for. So just like with infinite semi-infinite geodesics, the natural way to construct a one-sided geodesic is to take 2 points. One is fixed, and you take the other one to infinity along a certain direction. And this is the same procedure. It turns out to work very well for this model. And so this is my paper with Li and Li, where, among other more detailed results, we prove this, that once you fix a direction once you fix, first you fix a direction, then for almost every realization of the potential, if this point is taken to infinity along a direction V, then these point-to-point polymer measures converge to a limiting measure. So this convergence happens in terms of, well, first of all, in terms of finite dimensional distributions, but then also densities converge. Anyway, you have this convergence to some measure that is concentrated on infinite paths. And it turns out that this new measure that we obtained through this limiting procedure, it turns out to be unique infinite volume polymer measure concentrated on paths, on infinite paths with prescribed slope. So this gives you this thermodynamic limit. It gives you a measure on infinite paths concentrated on paths with the same slope, and it can be obtained by this limiting procedure.
So you're talking about taking x sub n over n deterministically to V, because I was thinking of the x sub n's as random, but I know you did some kind of.
Oh no, you can do that. So what I have said is that xn is fixed, it's a point. And I take this point to infinity, so n grows, and xn also goes to infinity. So the only restriction is xn divided by n converges to V. But instead of that, you could have considered a distribution. And if this distribution satisfies a certain law, if it satisfies the law of large numbers, as n goes to infinity, this distribution is also concentrated along a small cone. Then you will also have the same result.
Okay, so
it's not a part of this statement, but it is a part of the paper.
Okay, thank you.
Mm-hmm. Yes, beta is always fixed, and it is an essential for this. In this one-dimensional story, the role of beta is not important. It has to be positive. Thank you. Thank you.
Do you know the analog of the limit shape, the free energy for this? Is it explicit?
Yes, right. So the reason why this works, I didn't want to talk about this, but the reason why this works is because this is one of the few situations in the polymer world where the shape function is actually known. It's a part of this paper, and it's one of the critical tools here, that the shape function here is exactly quadratic. It's some constant plus v squared over 2, and that helps a lot, because you get straightness estimates, and you can get a lot of you can get estimates on concentration of this path and on the free energy. So it all works because the shape function for the free energy is exactly quadratic. Thanks. Okay, so it's in this situation that we know these descriptions that that for each direction v, there is a unique infinite volume polymer measure concentrated on paths with this slope v, and it can be obtained from this procedure. But in general, this is basically one of the biggest open problems in the field. So what happens if you change the energy a little bit? So what if it's not quadratic? What if the dimension is not just 1 + 1, but 1 + 2 or higher? What if the potentials are not IID, but add a little bit of dependence in time? What about lattice models? And so it turns out that these questions are largely open, except for a couple directions that I should mention here. And so this is the similar results have been obtained for log gamma polymers and for O'Connell-Yor polymers, including the 0 temperature case, by these groups of researchers. And it's not just one paper, actually. It's a series. Another thing that I should mention is that there is a PDE approach to the Burgers equation. So when I studied the Burgers equation, I really used these polymers and the variational principle in zero temperature. But there is a new PDE approach by all these people. So maybe eventually you can start deriving things about polymers from the PDE approach, but currently it's the other way around. So this picture where for each direction v, you have exactly one infinite volume polymer measure. So it's not known in general. And this is what I actually want to know. And I suggested to my student Hangbin to study these infinite volume polymer measures through stochastic gradient flows. And so the idea is actually to understand these general models, but so far we can I only have a story for you for the same 1 + 1 model with quadratic potential. So first of all, what am I talking about? In general, if you have a finite dimensional Gibbs distribution where you literally compute the density of your measure with respect to the bag using this standard Gibbs-Boltzmann formula, where z is just the normalizing constant, I should say this. So this z is a partition function. So it turns out that these measures that you can obtain like this, given pretty arbitrary energy function, it just has to go to grow to infinity. All this for each function e like that, this measure can be viewed as an invariant distribution for this diffusion. And so this is the stochastic gradient flow, right? So because the drift term is minus gradient of energy, and so it means that you're going from you're heading towards lower values of energy. But on top of that, there is a perturbation of noise, perturbation by noise, and So sigma here is not just arbitrary, it's related to the temperature or inverse temperature by these formulas. And so it turns out that, and it's a simple computation if you know what the Fokker-Planck equation is, that there is a one-to-one correspondence between, the notion of the Gibbs distribution, the notion of invariant measure for this diffusion, they are totally the same in finite dimensions. So what happens here is, so what is an invariant distribution, right? So this is this gives you a Markov process. If you start this process with some initial distribution, you compute the distribution at any later time, we want the distribution to be the same. If this is true, then we call this measure, this distribution, an invariant distribution for this diffusion. And it turns out that in this situation, you should really start your diffusion with this distribution, and then that distribution will not change under this Markov process. Sort of a part of this claim is the uniqueness. So this, if you just look at this equation, you can ask a question about existence and uniqueness of an invariant distribution. So this actually says that the only invariant distribution is given by this formula. Now, this is an example that everybody I hope everybody has seen. So if you take the energy to be quadratic, take it to be, say, x²/2, then the only invariant density for this equation, where minus x just computes the minus gradient of this energy function. The only invariant density for this process is this Gaussian density. So this is the simplest situation where this makes sense. But in infinite dimensions, what do we do? So now we can attempt to write this energy as a function of the entire infinite path, but this expression alone doesn't make sense because the summation, because you will get infinite numbers when you sum all these terms. We can still try to make sense of the diffusion. We can compute the gradient of this energy with respect to x. Because we can do this because of the local dependence of the energy. So these are just nearest neighbors interactions. So when you differentiate that with respect to k, what you're going to get is just this equation. I mean this drift term. So okay, small fk is just this minus gradient of the random potential. So this is also a random forcing. And when you differentiate this quadratic form, what you're going to get is the discrete Laplacian, and that's exactly what it gives here. And so, of course, the easiest is to write it like this, but you can also write it like that, and this sort of tells you that if you have this kind of drift, and if you so this drift pushes your polymer in a certain direction. So what does it like to do? It computes the average between. So take the k. So there is xk and there are neighbors xk minus 1 and xk plus 1, and this is their average. And so so the direction in which your polymer is pushed is so from xk you're getting pushed towards this average. So it has this like straightening or smoothing effect, as all Laplacians do. So in a sense, this is a heat equation with some nonlinear term, and this is a random nonlinear term that's given by the environment. And there is additive noise acting on each coordinate. Now this is obtained just as in a formal way. I just took this energy that doesn't make sense in itself, and I took its and I computed the gradient formally. And so now my goal is to answer this question: does Does this equation make sense? What do the solutions do? Are they well defined? Now we're in infinite dimensional spaces. So in which spaces are they defined? And how about the invariant distributions? Can you make sense of the invariant distribution? Can you equate the invariant distributions for this infinite dimensional model with the infinite volume polymer measures that were constructed in the previous work? So that's the question that we're going to answer. So this slide shows you, so that's our main equation that we are working with. It has this, you can say that this is the Dirichlet bounded condition, the Dirichlet boundary condition. So our polymer that is going to evolve, it's zero coordinate, it's fixed, but everything else potentially can travel around. And so this is the theorem with my, this is the main theorem of this paper with my student Hanbin Chen, who just graduated, and he's going to work with Hugo Deminil-Capin, studying this fall as a postdoc. So what we proved is that yes, indeed, this solution map is well defined on this space. So if you start if you prescribe an initial condition at time 0, and it grows in K at most linearly, then the solution makes sense. Moreover, this dynamics, this equation, it defines an order preserving continuous random dynamical system. So there is this notion of random dynamical system that involves these random maps. You sort of have a flow of random maps that are organized in like a cycle. But let me not go into details. Let me just say that the solutions make sense, and you have order preservation. So it means that if you have one polymer on this side and another is strictly on the left for all coordinates, then they will always be ordered like this under this dynamics. This is what we prove. The slope is preserved. So if you take any v, and if you consider paths, infinite paths with asymptotic slope v, then if you start your dynamics with this path, forever it's gonna have the same. The solutions will have the same slope. So there is a unique invariant measure for this dynamics. Once you fix v, so if you fix a value v, then there is a unique invariant measure on this set, and this invariant measure is mixing, and moreover it coincides with the infinite volume polymer measures obtained through this limiting procedure that I described in the beginning. And one final thing two final things I should mention is that there is the so-called one force, one solution principle, also known as synchronization. So it holds on S of V, and I will talk about that in later in my talk. Then I will explain what it means. And also there is a certain quantity that we call ordering by noise. So there's not just monotonicity, but there is also some additional ordering, and things that were not ordered initially, they get more ordered as we go. So in general, in infinite dimensions, the fact that Gibbs measures are invariant for the associated stochastic gradient flow, it's not very hard. It's just a limit of finite dimensional problems, really. So the finite dimensional problem solves the Fokker-Planck equation, and then the infinite one is really just the limit of that. But the other way around, that the invariant measures are Gibbs. So this is harder. There are counterexamples, and well, under some regularity conditions, it's still true. So somehow there's a lot of results in this direction, but none of them fits, well, our setting doesn't fit any of those results. So people assume either compact state space, or that the potential is not just stationary, but it really tries to push you towards the compact domain, and then things work. Things with log Sobolev inequalities work. So something like this. So I claim that our work doesn't follow from any of those results. But there are many more papers than I mentioned. Let me try to explain to you. I mean, I know this is taking you to some totally different places than the first passage percolation, but let me try to explain to you why synchronization of one-force-one solution is natural to expect in this problem. So suppose that there is no external potential. So F, the randomness is 0. And then my equation simply becomes this. So there's no external randomness here. So this is one. Well, I want to consider two solutions and see how they co-evolve. So I take two solutions. They solve the same equation. So this is that equation for X. This is the same equation for Y. I just take the difference, subtract one from another, and then this is the equation that the difference satisfies. And so this is just the discrete heat equation with 0 point pinned, right? So this is the Dirichlet boundary condition. And so the evolution tells you that, so you can denote this if you want by a new variable and just say that this is a homogeneous heat equation with 0 boundary condition. And so this difference converges to 0 because because this is what happens to with the heat equation. Now, the heat equation that maybe we are used to from some elementary courses, something like heat equation on an interval, maybe on a circle. So there you have a spectral gap and there is convergence. The convergence is exponential. Convergence to 0 would be exponential. But here, there are no spectral gap for this Laplacian on the discrete semi-line. And so it converges really slowly, but it does. And so it means that you start with two different initial conditions, but as time goes, they get closer and closer to each other. So they synchronize. And you can argue that it's not hard to see that actually the common invariant distribution that they converge to is actually the Gaussian random walk with the prescribed drift V. Say if they were taken, X and Y are both taken from this, say they have slope 0, then you will just have a regular Gaussian random walk with 0 drift as the limit. And this argument is true in any dimension. I mean, there's no really one-dimensional specifics, but actually we know that polymers behave differently in low and high dimensions. So there are localization effects. So it means that this heuristic argument is not universally useful. But anyway, it tells you that these different solutions tend to come together, and hence their long-term statistical properties should be the same. An important point in our analysis is this order preservation. This is something that I already tried to hand wave about. But so if you have two paths and one is strictly on the right of the other one, then for all positive times, this ordering will be preserved. And again, so there is a whole literature on monotone systems and invariant distributions for those. But again, because of the sheer non-compactness here, we cannot just take some theorem and use it. The next step, though, is that we are able to prove the property that we call ordering by noise. This is what it is. Suppose you have two initial one-sided infinite paths that our dynamics is defined on. And one has slope V1, and another has slope V2, and V1 is less than V2. And so it means that, of course, eventually V2 is on the right of V1, but there may be a finite part where they are entangled, where they overlap. They are not ordered in the right way. And we can prove that if you have such a situation where V1 is greater than V2 is greater than V1, then at some positive time, they will get monotonized. I mean, there will be a moment of time where the random solution started at this point, on this path. It will be totally on the left of the random solution started this red path. And the mechanism, the way we can prove this, we rely on the following property. And so this is the extra condition that I mentioned on my slide 4 or something on the external potential. I need the following condition that I'm going to state only roughly. On arbitrarily large rectangles, I want probability that this forcing F is very close to 0. I want probability of that to be positive. And so this implies if I have this, and if I assume this condition, then because of the ergodicity, we're going to see those rectangles. If something happens with positive probability, it's going to happen infinitely many times in the entire random landscape. So we're going to see this situation, and when the forcing is very low, it sort of means that you're almost solving the heat equation with no external forcing. And the heat equation with no external forcing, it does this monotonization. I mean, it requires an argument. I mean, all this requires arguments, but this is my goal in this talk is to tell a story and not to give you, not to torture you with technical. Okay, so this with probability one, what happens is that due to certain recurrence property that we can prove, so these two paths, so they travel around somehow, and then eventually they will get into such a situation, and this event of disentangling, it happens only with, I cannot say first that it happens with probability 1, but there are infinitely many attempts due to certain recurrence that I can prove. And so eventually they get disentangled, and that helps the ordering. Yes.
So those lines that you drew, are they analogs of characteristics, or the analogs of geodesics, or
well, so they are
competition interface?
So this no, you can say that they are realizations of directed polymers. So they are not related to characteristic. They are not related to anything. So you just take an infinite polymer with some slope, and the dynamics that I'm trying to talk about, dynamics is defined for these initial conditions, and that's all I know at this point. So you just take one polymer that goes like this, and another polymer that goes like that. If their asymptotic slopes are ordered, then eventually these polymers will also get ordered. That's the whole story here. Okay. So if I want to say that infinite volume polymer measures are the same as invariant measures for this stochastic gradient descent, one thing I can say right away, that's the easy part of the program, is that Gibbs measures are invariant. And because I have constructed one Gibbs measure, exactly one Gibbs measure per asymptotic slope. So I already know that there is a bunch of these invariant distributions. And they are ordered. So that's also what we know from the previous work. And now the question is, are there any other invariant distributions? So do I have more than that? And so it turns out that because of this ordering by noise, in the stationary, so this is a vague statement, and I don't want to go into precise statements really, although I will make an attempt. But in the stationary regime, all these polymers are going to be ordered. So the invariant distribution corresponding to this slope and to this slope, you can sort of order them element by element. And this is due to this ordering by noise. So if you take two values v1 and v2, and you consider the dynamics associated to these values, if you let's take a look at some concrete coordinate. I don't know, maybe like coordinate number 1, and we know that in the stationary regime, what we can obtain from these dynamics for this invariant distribution and for this invariant distribution. So there's always an order between them. So these will dominate those. And it means that possible values associated with V1 are all less than the possible values you can get out of this that are associated with V2. And so it means that now if you consider all these, all possible velocity, all possible slopes V, it means that the entire real line is sort of tessellated into these intervals, and you have a monotone map. So to each V, you can associate maybe an interval of possible values, maybe just a point. And there's this additional super important consideration that the dynamics is shear invariant. So it means that if I restrict myself to consider, if I restrict myself to pass with slope v1, and I consider the dynamics on these paths, and then if I apply the shear transformation to these paths and to the external potential together. And so shear transformation, the easiest is just to look at this picture. So each next line is moved by next Riemann. So in a sense, you can say that you are looking from a moving in a moving coordinate frame. So that's what the shear transformation does, or Galilean transformation. And it turns out that due to the quadratic nature of the self-interaction, the dynamics in S1 is just conjugated to dynamics in S of V2 by the shear. So if you had solutions with this slope V1, and if you apply the shear, then you will obtain solutions. You will certainly obtain paths with slope V2. But it turns out that what you're going to map into that will also be a solution of the stochastic differential equation that I'm talking about. And because they're conjugated like this, and because the distribution of the potential doesn't change, because it's a stationary process in X and it's IID in time in these layers. So when you apply the shear transformation, the distribution of the environment doesn't change. It's the same. And so it means that whatever happens for paths with velocity v1, sort of same thing happen with paths with velocity with slope v2. And this means that the distribution of all these intervals that I was talking about, so they're actually the same. And because there are uncountably many of them, the only way to fit them on the real line is if they all have, if all these intervals are just 1 point, it's probability 1. Because if there are uncountably many of them and they are positive with positive probability, and you have the stationarity with respect to V due to shear invariance, then there are just too many of them. So this is a lack of space argument combined with shear invariance. And so the conclusion from all this is that the probability that these possible values that are worked out by the dynamics, that they occupy a whole interval, that probability is 0. And so so it means that there's only one value, that there's only one value you can obtain from the history of the forcing. So this is, you see, I'm having difficulties here because I'm trying to explain a rigorous notion with these words that I don't have time for. But this is based on this general idea that I want to mention. I mean, this is totally from a different universe than this conference, but it's a very important notion in random dynamical systems. And so let me go through this slide. So suppose you have a Markov process that is generated by a random dynamical system. So you have, which means that you have this system of random maps, flow of random maps. And it turns out that if you have a distribution that's invariant for this Markov process, then I mean, your natural inclination to, if you want to study long-term dynamics, is just to start at this distribution, go forward. But it turns out that a super useful point of view is actually to go backward and start the dynamics from very long time ago, and then see what happens at time 0. So what is worked out by the dynamics from the past? In a sense, you are saying, if I want to study ergodicity or something like that, I want to say that I want to pretend that the infinite time is now, and I want to see what is the history of the forcing. What does it work out for the present time? And so this is what happens here. So you start with this initial distribution at time s, and that's long in the past. And then this is the random map, and so this is the solution map. So this notation means that this is the push forward of rho under this map, and you just see what is the result of the evolution at time t. If you started at time s, that was centuries ago with this initial distribution. So you will obtain some distribution here, and it turns out that you always have a limit as s goes to minus infinity. There is a simple martingale argument. I mean, so actually, basically, these measures they form a martingale, and there is always a limit. And this limit means that, as a result, you have a distribution that describes. So this is the distribution of possible values at present, given the forcing in the infinite past. So the entire history of the forcing. And what is called one force, one solution principle, it is associated. It describes the situation where these limiting distributions are deltas. So it means that given the infinite history of the forcing, what comes out as a result of this evolution at present is unique value. So that's why this is called one force, one solution principle. And so this is what we're able to check for this system that I showed you. And actually, you can upgrade this and not only obtain the convergence in distribution, but convergence point-wise. And you can make sense of the resulting limit as a global stationary solution. And this is a standard picture that explains the one force, one solution, one force, one solution principle. So this is the global solution that you construct in this way. And how do you construct it? You start with some initial condition long past, and you take this initial condition, you keep prescribing this initial condition at more and more distant past. And you see what comes out at the present. And in this situation, for these polymers that I'm describing, it turns out that there is a limit. It's just not a partial limit or anything. So there is a concrete limit x at time t. And then you can do this for all times t. And the result is that you have this whole red line of limiting values, and they are organized in a solution. So this is a self-consistent limit. So as a result, you have constructed this global solution for this random heat equation that I have been talking about. Now, if you think a little about it, it's not a trivial statement. I mean, if you have the heat equation, we know we cannot solve it backwards. So if I just give you some initial or terminal solution condition, from that condition you can't solve the heat equation in the reverse time. You will get something horrible. But this gives you a solution to a certain heat equation that is defined for all times. So sometimes they're called eternal solutions, but in the dynamical systems, in random dynamical systems language, this is a global stationary solution. So for my system, it means, what does it mean? It means that there is a unique value that's worked out by the dynamics from the infinite time. So you have the strong synchronization. And so it means that the statistics of all solutions in the long term are the same, which means that the invariant distribution can be only one on each ergodic component, which is the paths of the same slope. Okay, so this is the last slide. We believe that this picture, this theorem that we proved, that equates the infinite volume polymer measures with invariant distributions for stochastic gradient flows. We think that it actually should hold true for a very broad range of polymer models. All these non-quadratic interactions, high dimensions, all kinds of modifications of this model. In the discrete, in lattice polymers too, you can work with reversible processes that are similar to stochastic gradient flows. But it looks like at this point, my hope that introducing the stochastic gradient flows into the game, I hope to obtain a lot, like because originally I was sort of specializing in ergodic properties of infinite dimensional systems. So I wrote some papers on that, and you started getting this feeling that maybe because there was this tremendous progress in this area, that once you rephrase the important problems for polymers in that language, maybe there are solutions. So at this point, I only was able to work on the same quadratic potential case that already was known in the 1+1 dimension. I still hope that there will be some useful applications of the stochastic gradient flows in infinite dimensions, but somehow some time has passed, and not so sure right now. Somehow this is a lame ending for a talk. The difficulty in infinite dimensions, is the following. So you hope that the synchronization occurs, and so it means that these paths, they sort of get together, but because these paths that I have been talking about, so they have linear, like the main slope is linear, and there are fluctuations on top of that. And because of the KPZ scalings, we believe that they are fluctuating at the order of n to the 2/3. So is the dynamics, is the noise really strong enough to bring them together, and so that we can use some tools from the theory of infinite dimensional diffusions. So to be honest, at this point, I'm not sure. So this is the end of my talk. Thanks for this.
So you're in this last conjecture, in the statement for all V and R, are you suggesting that there shouldn't exist random exceptional directions where you could have more than one infinite volume Polymer measure?
I think, no, so what I'm going to say is it's not justified by any math, but I think that there are no exceptional directions for this model. But there's no math behind that I can give you to justify that.
So there's no analog of the competition interface, because in exponential last passage you do have exceptional directions.
Right, but there's zero temperature case. And, so I think things are quite smooth here, and I don't expect these effects to be present here. But you may be right. There may be something like that.
Shiva?
On the stochastic equation.
Here, where does the direction V come in the flow? Is it the initial sequence of points, or?
Right. So the equation itself,
Oh,
there's no
V.
V or anything.
that's right.
But then it turns out that if you fix a slope,
Right.
slope V, then if you consider all paths
Right. Yeah.
with that slope, and I denoted that set by S of V. So that set is invariant under the dynamics. So if you start with some slope, it always stays the same.
And also, do you have any assumptions on your capital F sub K? Because if it's superlinear, then I don't see it sort of.
Well, so there are some assumptions that Fk cannot F is a stationary process, and we need it to be tame in some sense. So there are assumptions. There are exponential moments, finite exponential moments assumptions on this F. But X itself, it's a solution. You start with some initial condition, and then we can prove that the solution exists forever and has the same slope. And moreover, they approach the distribution of the solution in the future. It approaches the unique invariant distribution. So that's what we can prove. But we need certain assumptions on the external potential.
Also, like the last question I
We
had
just
was
want that to be a stationary process that doesn't grow too far. But yes, it oscillates all the time, which leads to the serious non-compactness in the X direction. And then you obtain. I think your question was about X, but you have to obtain certain estimates on X. You start with. You have to show that your process X doesn't blow up. So yes, we have estimates like that.
And also, like that equation is well defined, right? So you can take the zero temperature limit for that equation, right?
I can take limit for this equation. What do you mean?
As sigma goes to 0, for example. Right?
Sigma goes to 0. Well, you can, but this is the resulting dynamics is not going to be sort of very interesting. So this is one of the many situations where adding noise actually gives you more meaningful dynamics than just non-random gradient descent. So this is one of those situations where there's no noise, these paths governed by this equation, they will just very quickly reach a close local minimum of the potential and then stay there forever. And that's not very interesting dynamics. When you add a little bit of noise, then this doesn't happen. And in a sense, the resulting random path, it explores, in a sense, it explores the entire S of V. So like all paths with the same slope will be sort of touched by this dynamics. And that's the effect of the noise.
So what I'm
Right.
So your ODE may not sit on one minima in some sense. Your noise might push it to the global minima. Is that what I'm asking?
So there is no. The notion of global minima here is tricky, right? Because we have this infinite path. So the global minimum, so that corresponds to this one-sided infinite geodesic or minimizer. So it means that it's a ground state of this for this Gibbs energy. It's a state such that if you perturb it locally, you can only get worse values of the potential. That's just one path, right? And in fact, we prove, so there's another paper by Lee and myself, where we prove that as viscosity goes, as temperature goes to zero, polymer invariant Gibbs measures, infinite volume polymer measures, converge to these infinite one-sided minimizers. Like what else could they converge to? Just that. But they indeed do converge. But that's not a part of this picture. It's a related but different question. Did I answer? Okay. Thank you.
Perhaps we should take other questions after the talk. So let's thank Yuri again.
Thank you.